Welcome to EDU World Space.
Given point P, we're trying to show that the total solid angle around point P for whatever shape we are integrating over is equal to 4 pi when the point P is within that shape. So we first need to demonstrate that it would be helpful if we can quantify 4 pi by a integration over a sphere. Since that would be quite simple, we don't have to worry about a change in radius. So we're going to have to demonstrate that the total solid angle integrating over a sphere is equal to if we integrated it over a cube or any other shape. So how are we going to do that? Let's first project a solid angle, and let's have it projected onto a very tiny region of the surface area of some shape. And we'll name this region ds. However, solid angles are with respect to the perpendicular area over the radius squared. So we really need to find the area perpendicular to the point P, given ds. And in this case, I'll put this as dA since this could be infinitesimal, and we'll just note this also on our solid angle equation. How we can equate this is by noticing that the perpendicular area with respect to P projected by ds can be projected by simply timesing by the cosine of the angle between the normal of the plane of ds and a line moving away from point P. But there's also something we can now note is if we just divide by r squared for both sides, we can relate that the solid angle on the left-hand side, which is really just for a sphere, is the same for the shape. So we basically justified that integrating over a sphere will yield the same quantity of the total solid angle as it would be for any shape. So now we'll just use the equation for integrating over a sphere. Well, first of all, we'll notice dA perpendicular is equal to some infinitesimal width times some infinitesimal height, which we can convert into coordinates of latitude or longitude. In the case of integrating over a sphere. So what we'll do is we'll set it as r d5 for latitude and r d theta for longitude, but then we need to times by sine theta, simply because as the longitude grid gets closer to the north or south poles of our integration, those lines get closer and closer together. And what we get here is r squared sine theta d theta d phi is equal to dA perpendicular. Okay, so that's what we're going to put up here from the top equals, let's write everything out we've seen so far, dA perpendicular over r squared. So now we substitute in dA and we cross out the r squares on the numerator and denominator. And we now notice that we have two integrals for a sphere, in particular half sphere, so we'll times by 2 and then integrate to 0 to pi and 0 to pi for the latitude and longitude. And then we have sine theta d theta d phi. So integrating over the sine theta, we would just get negative cosine theta and we put in values 0 and pi. And what we get is negative 1 minus 1 with the negative right in front, which just becomes 2. So let's do the 2 times 2, you get 4. And once you integrate the next term, you just get phi with a value from 0 to pi, which obviously 0 will not add anything. And we're left with 4 pi.